Hello everyone, today I'll show you how you can spawn objects on another objects that you spawn with PCG and some important things that you need to consider and some tips how you can make spawning more interesting and realistic and to have more control over where you spawn your objects. So for example, here on this wall with the door, this single object as you can see, but with my PCG graph I can control where I'm spawning these vines or ivy, let's say, by this material ID. So you can see that I can choose to have it spawning on the door or to have it spawning on the wall, or you can even change with the PCG and have it spawn on multiple IDs or have some other property that controls where to spawn. I'll show you all of this, and as you can see it works for any type of object, and you have even control how much you're spawning and if you want to spawn it from the top or from the bottom. So let's start working on this PCG graph. Let's save everything and I'll create a new graph so I can explain every step of the process. So let's go into our PCG folder and let's create a new folder, and I'll call it tutorial ivy, for example, because we're going to spawn this ivy on all our objects. So let's first start by creating a blueprint class, and it will be an actor. This will be the actor that we'll place in our level. And let's call it blueprint object with ivy. Let's open this blueprint and let's create a couple of variables that we'll need. So let's click on this add variable button, add the mesh that we'll need. Let's add the flip function that I showed you if you want to control is it going to place from the bottom up or from the top. So let's add another variable which we'll call threshold. It will control how much we are spawning of this ivy on top of our object. And lastly, let's create a material ID variable so we can choose where to spawn our ivy on our objects. Let's choose the proper type for each of these variables. So we'll start with the integer for the ID, float for the threshold, boolean for the flip, and static mesh for our mesh. This is the object that will spawn. And let's make all of these variables public by clicking this eye icon. And now let's add our PCG component into our blueprint. So click on the add component button and add a PCG component. If you don't have this PCG component showing here, you need to enable your plugin from the edit plugins and type procedural here and enable the procedural content generation framework. This will require an engine restart, and after this you will have this PCG component showing in the list here. So we'll create the component, and here into the graph field we need to connect the PCG graph. So let's right click into our content browser and create this PCG graph that we'll use. Let's call it PCG object with ivy. Same as the blueprint. Let's connect it to the blueprint component here, the PCG component into our blueprint. So drag it over the graph variable here and compile and save this blueprint. And now let's start working on our PCG graph. So let's open the PCG graph. It's currently empty, we just created it. So let's start with first spawning this mesh variable that we create it into our blueprint. So let's copy the name of our mesh variable. And let's just spawn one such object into our scene by creating a single point by create point. Let's create a single point into our level. The transform will be 0 for everything. The scale will be 1, so default value for everything. And the coordinate space will choose local component, so we can move where this point is created by moving our blueprint. So this will create a single point. If I place the blueprint into our level, like this, and if I hit the A key to inspect this node and open here the node that we just placed into the level, you can see we have a single point into our level, and if we move it, our position values will change. For example, here I'm changing the X value, now the Y value of the position, and now the Z value. So let's bring it back to the 0 value for the vertical direction. So now we have this point into our level. Let's spawn the object that we choose into our variable for the blueprint. So as you remember, we created this mesh variable. Let's copy the name and let's get the actor property here and spawn static mesh. And this static mesh will need this variable, so we'll get the mesh variable. Let's inspect this. It's currently empty. This is because we didn't connect any object into our blueprint. So let's select our blueprint into the level and let's connect some object, for example, this wall that I showed you. And now if we go back into our blueprint, you can see that if we inspect this node, we are getting the path to our object that we connected. So we need to connect this path to this static mesh spawner. We need an attribute into our points for this, so we'll add attribute. We'll call this attribute mesh, and we'll connect this attribute that we just get from our variable into our blueprint. And let's inspect this attribute. You'll see at the end we have properly appended this mesh attribute. So if we connect our add attribute to the static mesh spawner, if we choose the mesh selector type as a mesh selector by attribute, we can use this mesh attribute, so we can spawn into the level our object. So let's move our blueprint here. It seems that our floor here is not at the 0 position, so let's move it a little bit up. So as you can see, now we are spawning the mesh variable from our blueprint, and if we change the object that we connect here, we can spawn any mesh that we want. So this is a great start for now. Let's continue with our PCG graph. So after we spawn this mesh, we want to spawn on top of the mesh other objects. So we need to create a mesh sampler. So this mesh sampler, we need to connect a static mesh to this mesh sampler, and we don't want to have the same static mesh always because it will generate points based on this static mesh. So we need to expose this mesh as an input. So click the checkbox here at the top, and this will create an input pin into our mesh sampler, and we'll use our mesh variable to connect to this input pin. This mesh sampler is generating points, but they are not properly placed on top of our object still. So we need to copy the points that this mesh sampler is generating and place them on top of our object. So let's use our copy points command. We'll choose as a source the points from our mesh sampler, and as a target we'll use the position of our static mesh that we spawned. So let's connect our static mesh spawner to the target. And if we debug now the copy points, you can see that we are spawning a lot of points on top of our object. And currently we are spawning them with the default mode of 1 point per triangle. So this means that the denser your mesh is, the more points that you spawn. And for different objects, it's better to use some method that doesn't involve the actual geometry of your mesh, because if you use a mesh that doesn't have so much points, it will spawn smaller amount of points, and if you use a denser mesh, it will have a lot more points. So you want to have some predictability of how much points you're spawning. So let's choose the Poisson sampling. This means that it will have a more regular spawning on top of your objects, not based on the actual geometry of the object, but on the spatial value between the points. So here with this section on your mesh sampler, the Poisson sampling section, you can control how much points you are spawning. So let's reduce this to 3. And you can see that we are spawning much more points, but it is not dependent on the actual dense geometry on your object. It is creating these points based on a world units value. So this seems okay to me as a starting point. So let's continue with our spawner. So after we copy the points over our object, we want to spawn some objects on each of these points. So let's again create a static mesh spawner. And let's spawn our Ivy mesh. So let's create a mesh entry. Let's choose the descriptor, and here for the static mesh, we'll connect this Ivy object that we have. And if you look into our scene, you can see that we are placing this Ivy object on top of our regular wall object. Let me rotate it a bit to be a little bit better oriented to the light. So right now we have a lot of points over our objects, and we don't have the control that I showed you where we are spawning them, or the showing up only on the bottom part or the top part of the object. So let's create this part. For example, let's start with the material ID control. So here, before we copy our points, let's filter our points to only have the points on the part of the objects that we have. So let's do an attribute filter. And this attribute filter will need our material ID. So from our mesh sampler, if you go here at the extra section, you can output the material ID of the part of the objects where the point is being generated. So if I debug this mesh sampler node with an A key, if I inspect it, you can see that here at the end I have a material ID column, and some of the points are over part of the objects with the material ID of 0, and some are on top of a part of the object that have a material ID with 1. I want to filter all the points where I have specific ID, so I'll copy this getActor property and use the name of our variable from our blueprint, the material ID variable. Here I'll put the property name of my variable and I'll connect it to the filter. So this filter needs to check if our material ID property is matching this property that we connected here. So select the attribute filter, select the operator to be equal, target attribute should be the attribute name that you have in your mesh sampler. So you can see it generates this material ID property. Here into the extra section, you can control the name of this attribute, but I'll use the default one. You can copy it from here and use it into your attribute filter. So this will check if our material ID is equal to the value that we enter, and only after this will output all the points that match this filter. So now if I go into my level and look at the wall, you can see we are no longer spawning points on top of our door. And if I change the material ID, we are only spawning on top of the door. So this object, let me show you this object setup here. So it has two materials. The first one with an ID of 0 is the wall, and the second one is the material for the door. So that's why if we choose a material ID of 0, we are only spawning on the wall, and 1 only spawning on the door. And if you had some object with 3 materials, for example, let me find such object like this door. It has 3 materials, one for the wall, the door, and the window. I'll select my blueprint and connect this wall, sorry. And right now I can have a material of 0, 1, or 2, and this will control where we are placing our ivy. So you can create a different logic here. For example, after this filter, you can get all the points that are outside this filter and create another ID and match it to them if you want to have multiple IDs filtered. So I'll continue with this logic that I have here to have just a single material ID selected, and I'll bring back this to 0. So you can see we are only placing on top of the wall. And now let's create the logic that will place our ivy from the bottom or from the top of the wall, and it will reduce gradually to the other end of the wall. So to do this, before our static mesh spawner, we need again to filter the points in some way. So the way that we are going to do it this time, let me adjust here so you can see better everything. I'll disable for now the static mesh spawner. And now for this wall, let me connect back the previous mesh because it's easier to see with the other mesh where our points are. Like this. Okay, so right now I'm debugging these copy points, and you can see all of the points have density of 1. We are previewing the density value, and because all of them are white, this means that the density of all of them is 1. And you can see this by inspecting this node, scrolling here at the end of the data, and see that every point density is 1. So we cannot still filter the points because they're all with equal density. We need some way to create a different density and then to filter by this property. So we'll use a distance node. So this distance have the option to manipulate the density of your points. So let me stop debugging these copy points and start debugging this distance node, and we'll mark this set density option. And you can see that now if we change the value, we need a target for our distance to be calculated with. Let's choose the point that we had before spawning our static mesh. So this will be the target point that we are comparing to. So right now you can see that we started to have a different value for the density. It is currently a very small value for all of the points. And this value is controlled by this distance property here. And I find it a little bit hard to understand and control with this setup, the default one for the distance value. So I'll not use this set density. I'll use the actual value that it calculates, and I'll show you how to remap to density later. So the important thing that this density field is giving you is this distance column at the end. It is the actual value that it calculated from the generated point that you have on your object to the source point here that you started with. So this is the point that we are placing our wall. It's connected to the target of this distance node. And this value at the end is the value that is the distance between the point on our wall to this original point. And it is not actually evaluating the point itself, but it's evaluating to the bounds of the actual point that we create. So if we create here a bounds modifier and we connect this bound modifier to the target and we edit the bounds of this point, for example, I'll use the set value of this bounds modifier and I'll set the bounds of this point to, for example, have 400 at the x direction. And right now you can see the values here at the end changed. So if I connect here the regular point, I have some values here, and if I connect the bounds, I have different values. The point is still the same, but the bounds are different. This proves that it's using this bounds to calculate the distance, and this is a very important thing. So we can modify the bounds and control how they're used to calculate this distance. So to be easier to see into our level, let's create our graph to convert this distance field to actual density value. So we'll get the maximum value of our distance here with an attribute reduce node. So this reduce node will get the maximum value of our distance. So choose the max value here. Choose the density property. So if you inspect this point here, sorry, not the density, but the distance. If you inspect this node, you can see that we are getting the maximum distance of 297. Then after we get this value, let's divide the distance value that we have for each point. So here, let's choose the distance. And for the input 2, we'll connect this max value. And we have some error here. Distance does not exist from pin A. Yeah, this is because here I need to connect the data after our distance node. So now we have the distance from each point as a value between 0 and 1 because we are dividing the actual distance to the max distance. So this is creating a percentage value. And we can remap this value to have our value from 0 to 1 because for now you can see that it's from minus 0.6 to 1, and we need all our density values to be from 0 to 1. So let's again use this attribute reduce node. We'll actually use it 2 times right now. Let's connect it, and we'll use the minimum distance and the maximum distance. So the first one will be the minimum reduce value and the second one will be the maximum. And they are both work on the distance variable. And after this, we'll do an attribute remap. So we'll remap our distance value, and we'll remap from the minimum range of this reduce node here to the maximum range. So if I inspect this, you can see that we'll remap from minus 0.6 to 1, and our out range here will be from 0 to 1. So we'll remap all the values of our distance, as you can see here if I inspect the last node. If I arrange by the distance, it will be from 0 to 1. So we have a great value now for our density. So let's copy the attribute that we currently calculated here. So we'll copy the distance into our density. And if I inspect this copy attribute right now, you can see we are copying this value here from the distance into our density. They are the same after this copy attribute. So I'll use the debug node here at the last node. And you can see right now, it's a little bit hard to see over this wall. Let me hide this wall by disabling this static mesh spawner. And right now, it's a little bit easier to see. Our points are being assigned a value from 0 to 1. So the ones that are with value 1 on the top show as a white point, and the ones with the value of 0 show as a black point at the end. And let's implement the function that we had before to flip our points. So let's create a branch node here. So this branch node will use the actor property, so get actor property, and it will be our property flip, the one that we created into our blueprint here, this boolean property into our blueprint. So this flip value will control if we go through the branch A or branch B. So let's connect this static mesh spawner at the end here, and also we'll connect a density filter. Let's for now filter from 0.5 to 1. So if I debug this density filter instead of this copy attribute, you can see we are deleting the dark points and we are leaving only the white points generated of our object. And let's connect this output B again to this density filter, and we'll control which points we are keeping and which ones we are deleting with this flip property. So let's enable back our static mesh spawner here. Let's enable the static mesh spawner at the end and go back into our level and check how our flip property works. So if I click the flip value, it doesn't seem to work right now. So let's check our graph again. I'm not doing anything. I'm outputting the same value no matter what we do. So if I choose to go through the branch B, we need to change our density to be the reverse of the one that we have. So let's use the 1 minus node, and it will work on our density. So if we inspect our copy attribute here, you can see our density is 0.1. And if we inspect our 1 minus, it's now 0.8, because it's using this 1 minus operator to invert the value between 0 and 1. And this will be our output B branch. So let's go back into our level, and you can see this flip value controls if we are placing from the top or from the bottom. And now that we have this connected, I want to show you how the different options for our mesh sampler work and why we need to control the bounds of our modifier to calculate properly the distance and to have control of how we are placing these Ivy meshes on top of our object. So here into the mesh sampler, into the distance sampler, you can see we have these two settings fields, the source shape and the target shape. And in our case, the important part is this target shape. So currently it is set at sphere bounds. If I change it to box bounds, you can see that now we are using our bounds spatial box and we are not generating a sphere between the points of our bounds. So right now, if I change the bounds here, so for example, if I have it like 1, 1, 1, this means that my bounds for the point here is just a single unit at this position down here. But if I start to increase the x direction, so the x directions is the one pointing here at the end of the wall. If I go to 100, you can see that this bound starts to expand towards the other end of the wall. If I go to 500, 600, you can see the points that we are calculating this distance is changing. So for example, I'll go with 400, which is the size of our wall. Let's go of minus 100, each of the directions except the vertical directions, which will start from 0. And the bounce max, I'll put it 400 to work with this wall for this direction. Let's put 400 for the other direction as well. And for the Z direction, which is the vertical direction, you can see that if you change this value, you will change from where this distance is being calculated. So I want to start calculating from the bottom, so I'll leave it as 1. And the other important thing here at this distance node is this maximum distance. If I inspect this, let's go here towards the back of the component here, the distance attribute that we are calculating. If I arrange by this distance value, and if I start to reduce this maximum distance, let's put 100 for example, you can see that I'm no longer calculating a value over 100. And this is problematic for me because I want to have the full size of my wall. So I want the maximum distance to be a higher number of the size of my object. For example, 5000 is okay. This doesn't mean that it will calculate the value up to this distance. It is just a maximum. So our wall is 400 units tall. That's why the distance is about 400 from the furthest away point, the point at the top. And this maximum distance just needs to be further enough so this works as you intend. We are not using the density calculated by this node here, so I can remove this. And right now you can see our setup is taking care of remapping the density from a value to 0 to 1, assigning it by this copy attribute, and then we choose if we are using the top part or the bottom part. So the other thing that will make your spawning much more realistic is if you are reducing the amount of spawned object based on this distance. For example, if you choose to spawn from the bottom of your wall, it doesn't really look so realistic that you have a constant value of objects from the bottom to the top. You want to have a control how much this is extending on your wall, and you want to have the most of this spawning happen in the bottom and then gradually reducing to the top of this wall. So how to do this? So you can filter your density by adding another value here. So after you select if you want to place the objects from the bottom or from the top, then let's unplug this density filter and we'll create another logic here. We'll do an attribute noise. So this attribute noise, let's connect both branches, both sides of the branch to this attribute noise. So it will use some value, for example, the density, and it will output another value, which will be our random filter, let's call it. And this random filter will be set a value from 0 to 1. So if I inspect this node here, you can see at the end I have a random filter, a value which is from 0 to 1 randomly generated. And we want to do an attribute filter after this. And this attribute filter, let's connect both this value to the input and to the filter. So this attribute filter will check if our random filter that we just created is smaller than our density, or the other way around. Let's flip it. Our density is higher than our random filter. So this means that the bigger the density is, the closer the density is to 1, the chance of being bigger than this random filter is greater. So if we connect this to our static mesh spawner, you can see that at the bottom we have a lot more of this ivy being generated, or if we flip, it's the other way around. At the top we have a lot more than this ivy being generated, and at the other end it's gradually reducing, because the smaller the density is, the chance is higher to be discarded from our selection by this attribute filter. What else we can do to make this a little bit more realistic is use our threshold property that we created here into our blueprint. So let's copy the name of this property. Let's get actor property and paste the name here into the property name. So we'll use this threshold. We'll create an attribute noise again. And into this attribute noise, we'll not generate the value from 0 to 1 as before, but we'll generate the value from 0 to the threshold attribute that we created. So this means that this threshold will control how much is the maximum value of our generated noise here. And this noise will generate from the density and will not use the set value, but the multiply value. This means that we'll generate a random value from 0 to the maximum threshold, and then we'll multiply it by the current density. So this will reduce the density of our points by a random value between 0 and our threshold value here. And after this, we'll do a density filter, and we'll filter all the value below some point, for example, 0.1. We'll leave all the values between 0.1 and 1. This means that after we multiply these values, we'll create at some places random points that are discarded from our point generator, and they will be discarded by this density filter. So let's after this do again attribute remap as we did before, because our values here, if we inspect this density filter, I cannot see any data right now because this threshold is currently with a value of 0. This means that all our points are discarded. So let's go back into our blueprint and create a default value of 1 for our threshold. So let's compile this. Let's save the blueprint. And if we go back, now if we inspect our density filter, you can see that we have now points that are still being generated. And if you arrange by the density, you can see there is no density less than 0.1. Because all of the density that we multiplied by this is now being filtered from our object. So let's connect this to see it better into the level. And let's change this threshold. So if I change it to 0.5, 0.1, 0.2, you can see that we are properly limiting the range that we are placing these IV objects. So after this density filter, if we enter the threshold smaller than 1, so for example, right now I have 0.5, you can see that if we inspect this density filter, we now have density between 0.1 and 0.5. We have no bigger value than our threshold. And that's why I created this remap node here. I want to remap the value from 0.1 because we know the smallest value will be 0.1 because this is the values that we exclude here. So the in range min will be 0.1 and the in range max will be our threshold because we will have no bigger value than this threshold. So we'll remap the values from 0.1 to this threshold to our proper range from 0 to 1, and this will return our proper value of our density from 0 to 1. We will use the full range of 0 to 1 for our density. And what we'll need this range, for example, we can multiply our density. Let's choose our density, and here the input source 2 will be our scale, and the output target will be our scale again. So this will create smaller objects the more that we go up to our end of this threshold here, because the values of our density are reducing towards the top of the wall. So we will decrease the size of our ivy the further away it is from the origin. And it is maybe a good idea to have some minimum value. So for example, let's do a clump min. So we'll create an attribute here of a 0.5 and clump our values to this 0.5, and we'll connect them to our input A here of the multiply. Input B will be the regular points. And now you can see that we are reducing the scale of our objects. It seems that they're all too small. So let's see what's happening here. So our density is from 0.1 to 0.4. We haven't chosen properly the values in our clump pin. That's why, because it's not working. So let's choose our density into our clump min. This means that we'll clump the density from 0.5 to 1. Let's check the values of our remap. So our density is from 0.1 to 0.5, so it doesn't work as well. So here I need to check the density value. So okay, now the density is from 0 to 0.85, so yeah, the maximum is close to 1. So we are then clumping, and then we are scaling by this value. So the density, as you can see, is never smaller than 0.5 because of this clump. And then we are spawning our static meshes. So in this way, right now, you can see that you can control how much of this ivy you are placing on the wall. And it is looking a little bit small to me still. So let's check our graph. Or let's add at the end some transform points and connect this transform point to the static mesh spawner. So we'll add randomization of the direction, so 0 to 360 into our rotation randomization. Let's add some position randomization by entering some values to the offset here. So let's do -5 in X and Y to 5. And let's do a random scale 1.5 to 2.5. So now we have bigger ivy on our object here. Okay, so let's save this and let's test into our level. We can control by this flip property, is it starting from the top or from the bottom? We can control by this threshold how much are we spawning. And this map ID controls if we are spawning on our door or our wall. And as I showed you earlier, no matter what objects do you place into your level, you can see that it's working the same way. You can control the density of the spawned ivy, you can control is it on top or the bottom, and you can control the material ID on which it's placed. So for objects that doesn't have this material ID property, I mean they do have it, but they have just a single ID, like this bench here, which is coming from the free environment pack on the FAP called Park environment, I believe. So this bench doesn't have two material slots. So what you can do is edit the bench, create two material slots and put the same material in both of them. How to do this? Just duplicate the objects that you have for the bench. So right now you can see this is the original bench. This one, the one I edited earlier, and this is the one that I created now. So this one still has just a single material slot. Let me go into the modeling mode, and into the modeling mode, select this attributes section and edit materials. So into this section, you can select here. The selection mode by default is brush, change it to UV island. And if you click on some objects, this will select them by having this color goes red to show you it's within the selection. So you can select all the objects that you want to have a different material. For example, I'll select the metal parts of the bench at the both ends, like this. So to have this to be with an additional material, let's go here at the section at the left into the modeling tools, create another material, then select the newly created material here into the active material, scroll down and click on assign active material. So this will create different SWOT into your object. So let's click accept. It will generate this bench with additional material SWOT. And here into this material SWOT, you can just put the same material as the other SWOT and the bench will look the same. But if you use it into your PCG graph, so let's use this newly created bench. It doesn't have this material applied, so let me just quickly apply the material to the actual model of the bench. Let's save it. So right now it looks the same, but you can choose if you want to place your ivy on the part of the bench that is with these wooden boards or the metal parts at the both ends by changing the material ID. And by flipping, you can control if it's at the bottom or at the top. So this shows you how you can control the placement of objects on top of another objects created with PCG. So you can see that you can even edit some objects to have them give you more control. How are you placing PCG objects in your scene? You can have different control. Instead of having this being controlled by the material ID, you can choose any of the other properties that you have to filter here. Instead of this attribute filter to be by material ID, you can use, for example, this mesh sampler UV attribute. Instead of doing the extra section here and using the material ID, click here into the extract UV attribute, and this will extract two attributes here for the UV X and Y, and you can filter by them, or you can do any other manipulation of the data in your PCG graph and filter by that. So I believe this shows you how much control it gives you to place objects conditionally into your scene and have values created to control that into your blueprints. So hopefully you like this tutorial. If you have some questions, write in the comments. You can join the channel. This will help me a lot into creating more tutorials, and I'll make sure to add some content for the channel members. If you join into the higher levels, you can watch the tutorials earlier. And guys, I'll see you in the next one. Bye.